All right, let's start. Good morning. How was the midterm? I tried to make it harder than before. It was harder, yeah. Yeah. Because, I mean, the end of, so for the first midterm, like I said, it's like there were like 11 or 12 perfect papers. And when something like that happens, the general assumption is that there's always like a, Gaussian distribution. And it's like, when the exam is too easy, what you end up doing is that just like with, audio, it's like you're peaking and you're losing information somehow. That's why I tried to make it harder this time. That I hoped would affect the top of the class more compared to the bottom of the class, in terms of grades, of course. But we'll see. By now, I don't really try to punish people with performance and stuff. And I'm also aware that, this classroom is not quite appropriate for exams. I hate that I'm subjecting you to that whole situation. It's, is what it is, unfortunately. Okay, so this week really is the starting point of the last part of the course, okay? This week we're going to start talking about eigenvalues and eigenvectors. And essentially the rest of this course is all about these eigenvectors and eigenvalues. So, evals, evx, and there's a bunch of things that is like downstream from these. Spectral theorem, singular value decomposition, orthogonality, one final version of the so-called rank nullity theorem. These are all going to be downstream from these. And then if time permits, we're going to transition to applications as well. This is, eigenvalues and eigenvectors is the main export of linear algebra at the basic level, okay? We have developed all the computational tools that we're going to need. But you see, things are getting faster. I'm doing less and less calculations explicitly. Even though, things are going to get slightly more sort of advanced in terms of calculations and so on. So you're going to need to, eyeball certain calculations to be able to do things faster. Ultimately, at the end of the day, even though you might be sort of getting confused about the concepts, it all, again, boils down to row reduction, and even determinants boil down to row reduction if you force it, okay? So we have this final item in relativity that we were talking about. And this has like multiple instantiations, in fact. And I'm going to start with this active versus passive distinction. How many of you have seen something like this before? Active versus passive. Okay, we'll talk about it. This is a very important idea. Because so far, we were, developing relativity. In other words, we were developing this basis conscious thinking or calculation or computation in linear algebra. And then we realized, there are vector spaces. These are sort of things out there that we don't quite have control over. But if I have a basis is basically my pair of glasses or my window or whatever, or my measurement apparatus. And so I go out into the world, use my basis, in other words, my measurement apparatus to measure things. Now I have a bunch of numbers. Hi.
I cleaned the whiteboard.
Thank you so much.
Tomorrow is Tuesday, everybody.
That is true.
Have a good day.
Thank
Spring
you.
is coming, everyone.
Yeah.
March, April, May. So, is everybody excited about spring?
Yeah.
Have a good day, everyone.
Thank you. So, what were we talking about? Okay, we introduced how we have these two different things. There's the world out there and what I perceive of it. And we sort of split these two. of course, this kind of sounds philosophical, and it is philosophical, but the nice thing about math is that even though from a philosophical point of view, your humanities friends could have objections, from a mathematical point of view, you can pretend either way, so it doesn't really matter. It does matter, though, somehow, when it comes to certain design choices. And so I want to first talk about this distinction between active and passive transformations. Because, so this really comes into play when you're starting to deal with some sort of a user interface. Okay? Here's what I mean. I'll start with an example. Say you have a PDF file, okay? And you have a screen. Probably, if the PDF file is large enough, you're not going to be able to see the whole thing. Say this is your whole document thought of as like one scroll. And your screen, this is the whole doc. Say this is your screen. Okay? Meaning you're able to see only this part, what's in the middle. And so there's some text here. I'm just going to call it X. There's some text Y, some text Z. Okay? Now, of course, you want to keep reading. You want to sort of look into the parts of the document that you're unable to see at this current position. Okay? You want to see what's in the introduction or what's in the conclusion, whatever. Let me just check. Okay. So, assuming, for instance, you have like a laptop, even that changes depending on the thing, but say you have a laptop and you press the up arrow, okay, to change what you're seeing, okay? If you're using Windows or whatever, I believe if you press up, you should be seeing X now, okay? So pressing up means I want to see what was before. Okay. But for instance, if you were looking at the same document in your smartphone or tablet, whatever, swiping up would correspond to seeing what Z is. I mean, swipe up, you see Z. Does this make sense? Of course, this is a choice. Typically, you would go to the options of whatever app you're using, and it would allow you to sort of dictate what up should mean. Right? So you can sort of change this. But ultimately, these two is, so the distinction between these two is the distinction between an active and a passive transformation. The first one is what is called an active transformation. This one is a passive transformation. I hope I said it right. Yes. No, it's the other way around. I got confused. See? Yes, it's the other way around. Sorry. It is confusing, this stuff. This is passive. This is active. Does this make sense? Hold on a minute. Okay, this matches with my notes, but I'm getting confused. the idea of a passive transformation should be the following, okay? The observer moves, and the world itself does not move. Okay, yes, okay. This is correct. So the idea is this. With the passive transformations, I'll write it here. The world has changed, but the observer did not move. Whereas for an active transformation, it's not the way around. Sorry. This is the active transformation. Yes. It's one of those days. Apologies. Every semester I end up making mistakes like this. This one day. Active, observer, did not move, the world moved. Okay. The world has changed. The observer did not move. Okay, this is the active. The passive is the world did not change, but how I looked changed. The world stays the same. The observer changed. Exactly. Okay. Apologies. Why do you call these like this? So imagine your screen is the observer, and the world out there is the PDF file that is like laid out flat like this. In the passive case, pressing up really represents, move the observer up. Take the screen, move it this way. Okay. So imagine XYZ is fixed. Move the screen up. Okay? Now it makes sense. Whereas in the active case, when I say up, I really mean the world. Take the scroll underneath, keep the screen fixed, move the scroll up. Okay? Pull the scroll up. That's why it's active. So if you're moving the scroll, or if you're imagining that you're moving the scroll and fixing the screen, that's an active transformation. You're actually doing something out in the world that causes a change, which consequently causes a change in what you're observing. That's an active transformation. On the other hand, if you're thinking, oh, what is happening out there is fixed, but I'm just looking at a different part of the world, that's a passive transformation. Okay? So similarly, imagine you're sort of, you're trying to design the screen in an electric vehicle or something. I'll just do something like this. Okay, that's you, and there's the world out there, and you have this cone of things that you can see. Say you have here a tree, and here a house, and here, say you have a car. Okay. Now you need to assign what it means to turn right. Okay. When you turn right, you're going to say, oh, the passive transformation would say, I'm literally looking rightwards. Okay. I'm not changing anything in the world. I'm literally changing myself. When you're changing yourself, how you're observing things, that's passive. On the other hand, typically in video games, for instance, instead of changing the observer, you're actually changing the world. Right? Turning right really means take this world and turn the world so that for the perspective of an active transformation, turning right corresponds to now displaying the car. From the perspective of a passive transformation, turning right corresponds to now displaying the house. Okay. This is again like a big thing in the context of navigation systems and so on. Imagine you have a plane, because even within the plane you need to have some sort of like a sensors, whatever, and so you need to be able to say to the pilot how the plane is moving. While of course out in the world the plane itself is moving or turning right or left, whatever. From the perspective of the screen that the pilot is seeing, typically you move the world and you fix the plane. So that's the distinction between active and passive. Okay. And so why is this an issue? Well, it's not quite an issue. It's just something you need to fix. This sort of trickles down in the math level into sort of either left multiplying or right multiplying, whatever. So in terms of the math, it gets somewhat confusing if you're sort of confusing which one your program is based on. Because ultimately, from the mathematical point of view, these are interchangeable. Right? So if you want to ultimately display x, well, from the passive perspective, you press up. From the active perspective, you press down. Okay? So depending on which paradigm you're using, you're sort of inverting your matrices underneath the hood. Okay. And this is all part of relativity. When we were talking about linear transformations so far, we were really thinking of active transformations. I didn't say this, but that's what we were doing. I was like, okay, here's a shape. Okay, here's a face in the plane. Apply this linear transformation to it. Now it changed. And we were essentially thinking of the same basis. And so here's a more specific example. So for instance, imagine A, let's say 1, 1, 0, 1. That's a shear transformation of the plane. Right, so A as an active transformation versus A as a passive transformation. Okay, as an active transformation, it does this. So 1, 0 is stayed at is kept at 1, 0, and then 0, 1 is sheared to 1, 1. You know this now, like so. That's an active transformation. Why do I get to call this active? Because something is happening, and really, when I'm drawing these axes, I say to myself, even when I assume that my observation apparatus doesn't change, I see a transformation. So relative to the standard basis, I'm saying A takes this, transforms it to this. And if I'm keeping my basis, I'm going to see a change. Okay? If I were to think of it as a passive transformation, I would pretty much draw the same thing, except it would look like this. Okay. What is the difference between these two? Well, this says that actually what I did was imagine this sort of a stationary picture on a sort of like a flexible material. You're sort of like shifting it sideways. And so the shape itself did not change, but how you're seeing it changed. And so underneath the hood, this is actually not doing anything actively. All you're doing is you're changing how you're seeing things. Okay? So this is, okay, I've caused an actual change in the world. This is, I'm just changing my perspective of what things are. Just taking off my glasses, whatever. Okay? And so this is, this would correspond to the idea that you take this matrix and you interpret it as a change of basis matrix. Okay? So the passive case, interpret A as a change of basis matrix. This stuff gets really confusing, as you've seen. I got confused with passive and active also. And of course, in general, probably both happens, right? So typically it's a mixed transformation because let's say you're trying to observe something physical, but insofar as your measurement apparatus too is physical, probably it's also being affected by what is happening physically, which means not only is something happening actually out in the world, but also even if you were using the same apparatus, in time, things happen to the apparatus itself. Maybe it is degrading, whatever. Okay? And so when you're measuring something, you need to be able to distinguish which part of that measurement is coming from the passive transformation and which part of it is coming from the active transformation. Okay? So let's try to give more specific examples. I'm going to introduce a formalism, which is essentially this idea of the matrix representation of a linear transformation that I wrote over here. And this idea somewhat incorporates both. And the mixed case as well, which also allows you to split it however you want. The main idea is this. Say you have two vector spaces V and W, then any choice of bases for these spaces trickle down to some choice of a basis for the space of linear transformations between these two. So let VW be finite dimensional vector spaces. Say beta is a basis for V, and say gamma is a basis for W. Beta. Just going to use ordered bases for this. Basis of V, and then gamma m many vectors in W, a basis of W. Okay, let's remind ourselves, what does this mean? This means, well, first of all, don't worry about this tuple notation. All I'm trying to say is that the order matters. Okay. Beta 1, beta 2, beta n, whatever. These are all vectors in V. Okay. they are linearly independent, and they span the whole space. In other words, given any v in V, any vector in V, I can display it uniquely as a linear combination of these vectors. And likewise for W. I'll write these. This was the content of this unique representation theorem. So, any V in capital V is a unique linear combo of BJs. Right, so B equals sum where j runs from 1 to n, say Cj beta j. If you were to fix scalars, C1 to Cn, this defines a unique vector. And given any vector in this abstract vector space, there are unique numbers C1 to Cn such that B is exactly this linear combination. That's the content of this unique representation theorem. And likewise for gamma, I'll write this here. C, let's say D, I, gamma, I. Okay. Now, based on beta and gamma, I want to come up with a basis for the vector space of all linear transformations from V to W. Basis of, this was the notation that I introduced. This is the vector space of all linear transformations from E to W. Vector space of all linear ops from V to W. And I want this basis to be compatible with these two bases. How do I imagine this? Well, V for me is one sort of static world. W for me is yet another static world. And this L of VW is the collection of all sort of transformations from one static world to the other one. I would like to be able to measure transformations from V to W in a way that is compatible with my original measurement apparatuses. Okay? So a basis like this, compatible with beta and gamma. And here's the idea. If I were to take a vector in L, in other words, a linear transformation from V to W, is arbitrary, what do we have? Well, I'm just going to feed to it some V, which by the uniqueness theorem is of this form, and I'm going to try to do something. Okay? So T of V replacing C j beta j of course this is a linear transformation, which means by definition it distributes over linear combinations. Okay. But then, for each j, beta sub j is a vector in V. If I apply t to it, now this is a vector in W. But then by the unique representation theorem again, for each j, I should be able to expand T of beta j as a linear combo of gamma i's. So I'm going to have coefficients here, di, but they're going to depend also on j. So I might as well write it as aij times gamma I. These are finite sums, so you can reorder. Okay. Then inside I have j, 1 to n, a, ij, cj times gamma I. Okay. I realize this is kind of nasty, keeping track of these indices and stuff, but this is essentially how you do these kind of things. It's not that important for us, but I think it's good that you get exposed to these kind of things at least a couple times in this course. Because in applications, you end up needing to start using indices efficiently like this.
May I ask you a question?
Yes.
Will this work regardless of the dimension of V and W?
As long as they're finite. But yes. Yeah, you can also think of it like that too. It's like you don't want to hard code the dimensions to 3 to 4 here, whatever, because yeah, in principle, you want n to be possibly like 10 to the 10 to the 10 to the 10. Okay. Any other comments or questions so far? What does this tell you? Well, it's going to tell you something more important also. It's going to tell you the matrix representation. But at first glance, you see, your inputs are completely determined by CJs, by the unique representation theorem. And your output, relative to T, is therefore completely determined by this expression as a linear transformation of Cj. Underneath the hood, this is a matrix vector multiplication written in indices. Okay? So, if you want to sort of wrap up this whole discussion, the appropriate basis for the space of all linear transformations from V to W, compatible with beta and gamma, would be this then. The appropriate basis of the space of all transformations from V to W is this. So let's write it like this. Okay, T, let's say PQ, beta J goes to gamma I if I believe Q is J, P is I, 0 otherwise. These PQs, where P and Q run from between the appropriate indices, gives you the basis for the space of all linear transformations. It's kind of hard to keep track of. The way I think about these things is like so. Well, I say to myself, this V and W are supposed to be these abstract vector spaces. And if I were to take a linear transformation from V to W, that should be something hard to control for me. But what I can do is I can transition to the matrix world using the beta basis for V and gamma basis for W, and just do some sort of a matrix-matrix multiplication. Before going any further, I think I should do an example. This is kind of getting overwhelming, I realize. So let's look at this case. Okay. Say I have two bases. Say one of them is the diagonal basis. Let's call it beta. 1, 1, and 1 minus 1. So I guess we had denoted this by tau before. Let's also use the standard basis. Why not? That was a standard basis. This was a diagonal basis. I'll write it here. Remember, relative to sigma, the matrix representation of a pair xy was just a xy vector, or rather a matrix, like this. And relative to tau, the diagonal basis, the representation of xy was the average and the average of x and minus y. These we had computed before. And so, for instance, I can look at this. Say I have an A here. M sub sigma. Okay. Say my A transformation is given by this. Maybe I should use the letter T so that it matches with what we wrote over here. T for transformation. I want to have a linear transformation here. Say it is 2x plus y, and then y. And then x, let's say. You see, I'm describing my transformation in terms of what it does to pairs. But I want to come up with a matrix now. I want to represent my T as a 2 by 2 matrix. Because ultimately, even though out in the real world, right, so this is my real world, so to speak, T is something that takes pairs of numbers, transforms them into pairs of numbers. I want to measure, and instead of using pairs of numbers, I want to look into column matrices, and therefore I would like to be able to represent T as a 2 by 2 matrix. Represent T as a 2 by 2. Well, you see, I'm just going to see what this does. If I were to start with an xy here in this diagram, if I were to apply T to it, now it's this guy. This is something that happened out in the world. It's an active transformation. But I want to represent these using my bases. Using the standard basis, this is xy as a matrix. And for whatever reason, the output space I'm measuring using the diagonal basis. Okay. So now what is this? The first entry is the average. So that's let's compute it here. Divided by 2. So this is 3 over 2x plus y over 2 is the first entry. And then if I were to take minus, now this is this. Which means if I have this active transformation and simultaneously with this active transformation, I'm also changing how I'm measuring things from the standard basis to the diagonal basis. Somehow, these two active and passive transformations are going to sort of get together. And in the appropriate matrix multiplication, it should be this. I'm going to see effects of both of them. Namely, this matrix is going to be what? 3 over 2, 1 over 2, 1 over 2, 1 over 2. You see, in your measurements, you're seeing, so there's some contribution coming from the actual active transformation that you're applying, but also for whatever reason you decided to change your basis along the way. The input space, you're measuring relative to the standard basis. The output space, you're measuring relative to the diagonal basis. Well, if you're changing how you're looking into the world, well, that's going to affect the calculations, possibly. So this is a mixed matrix, if you want, both an active and a passive transformation simultaneously. If I were to use the same basis for the input space and the output space, that would be a pure active transformation. I'll write this here first. Active plus passive. Yeah.
Is the bottom right entry going to be negative 1/2?
No.
Okay.
Why? Because take this, subtract this to it, this from it, is x plus y divided by 2. Yeah. Yeah, if you want, you can sort of write instead of x u here, and instead of y, you can write v. Yeah. So that's a mixed transformation situation. And to represent this idea, I might write something like this. Just like we write, oh, the matrix representation of this vector, which is out in the world, relative to the standard basis is this, relative to the tau basis is this other thing. I might write this as the matrix representation of t, and I'm going from sigma to tau. This is the notation I use. This is not very common as far as I know. I kind of like it because it kind of multiplies nice and stuff. There are like nice multiplication properties. You can use whatever notation you want to use as long as you can keep track of what is actually happening. So if I were to use, for instance, sigma on the input, sigma on the output, okay, I'm saying this time I'm not changing my measurement apparatus, but there's still something that I'm doing out in the world. But of course, instead of this tau here, if I had sigma, this I would store as 2x plus y and x, which means that the matrix representation would be what you're accustomed to. Okay. I could have done it the other way around. I could have looked into tau to tau, for instance. That would have worked also. In fact, I'll leave that to you to compute. Now the wonderful sort of multiplication property of this notation, which is also the reason why I use it, as far as I know, I came up with this notation, but someone else might have come up with it also. It multiplies really nice. So say you have one basis for V, another basis for W. Oh, I'll write it somewhere else. It's going to take a larger space. Write it here. VW, say Z, is a basis of, well, X. 3 vector spaces. Say I have 2 transformations, one from V to W, another one from W to X. And I'm trying to basically composite the 2 matrices, or the 2 transformations. But somehow I need to store things in such a way that the corresponding matrix representations, when multiplied together, correspond to the matrix representation of the product matrix. It's a mouthful. So I have this situation. Say this is A, this is B, this is BA. Then I have this. Oh, delta. So beta to delta of BA is gamma to delta of B, beta to gamma of A. Ultimately, how do I think of this? As long as I keep track of the different bases, I can take composites of 2 linear transformations like this, and I can pretty much turn everything into matrix-matrix multiplication insofar as I'm careful with, well, measuring the output of A and the input of B with respect to the same basis. Otherwise, what might happen is, even though the matrix-matrix multiplication works, because you're sort of messing up the way you're observing things, the end result ends up being a matrix that really has not quite, so that has some sort of observation caused effects. So it could be a mixed. What I was trying to say here is that both of these are purely active transformations. These are purely active. And likewise, if for your T, you take the identity transformation, and all you're doing is changing a basis, that's a purely passive transformation, and that's a change of basis matrix. I'll write that too. This is, and this, and the other one. Change of basis matrices. I'll leave these to you to compute. And these are purely passive. Nothing is happening. You're using the identity transformation in the world. Okay. So that's about it. This takes a while to get accustomed to in terms of calculations, and probably in the next problem set that is going to be whenever you're going to see some problems about this also, but we're essentially done with relativity. Thank you. All right, let's start. Good morning. I'm going to take attendance today. So we still have a couple of things to discuss regarding relativity. I had started coming up with this matrix representation of a linear transformation yesterday, and then the indices and stuff got rather overwhelming. But I want to finish that discussion, give perhaps one or two examples, and then we'll be on our way talking about eigenstuff. And another thing too, I wanted to discuss more digital signal processing, the signal space, whatever. Probably for now, I'm going to set that aside. Depending on whether or not we have time, I might fold it into other things. But, it's a beautiful subject, and I quite like it, but we'll see. We'll see. So, what were we doing? We had two finite dimensional vector spaces. Say the dimension of V is n, and the dimension of W is m. And we had a linear transformation from V to W, linear up. The point was, we fixed a basis for V, called it beta, and we fixed a basis for W, called it gamma, and ultimately we wanted to represent T as an m by n matrix. So what do I want? I want to represent T as an m by n. Okay. And so this representation should match with the basis that we chose. And so I think some of you had looked into this sample midterm 2, from the last time I taught this class, and one of the problems was represent the transposition operation as a matrix. So for instance, we talked about a bunch of sort of linear transformations that are not, at least a priori, given as rectangular matrices. But then how do you sort of represent more complicated linear transformations as matrices? For instance, in polynomials, how do you represent differentiation as a matrix? Because why? Ultimately, even though there are more complicated linear transformations compared to the ones that we're used to, we still would like to be able to think of them pretty much as matrices. Okay? So I choose a basis for V, and I'm using these numbers n and m to match with what we're used to. N is the dimension of the input space, m is the dimension of the output space, for instance. Gamma is going to be a basis for W. I want the so-called matrix representation of T from beta to gamma, okay, to be an m by n. So this was the notation I used. I think in the textbook, the notation is something like this. So T with an arrow like this or something. So T, maybe something like this in the textbook. You can, of course, use whatever notation you want. You could also see something like this. It's also very common to see maybe something like this. T with maybe beta here and gamma there or something. There's a bunch of notations for this. It's not really standard. OK. And so how should this work? Well, if I start with this t, what should happen is I take a wild vector in V, input, represent it as a column matrix using beta. That was our notation. So now this goes into the space of n by 1s. And here I represent an output using gamma. Okay. And so ultimately, this matrix representation of T relative to these bases should fit into this. Right? I have an n by 1. I would like to be able to take this A matrix, left multiply. So maybe I should say left multiply by A. I would like to be able to take my n by 1 unique representation of a wild input vector V, left multiply it using A, which is supposed to be an m by n, which ultimately should give me an m by 1, which again should be the matrix representation of the wild output vector T of V. Okay, we just keep track of these coefficients. So you feed something like this. Okay. Under the matrix representation, now this turns into C1, C2, whatever. Cn. If you apply T to it, this turns into TV, which I think we wrote it like this yesterday. J from 1 to m, and then I from 1 to n, Aij, Ci, gamma j, which then, if you store it into a matrix, you're going to have this as j runs from 1 to n, 1 to m, sorry. So when j is 1, for instance, I get the first entry, which is this ai1 ci. Second entry is ai2 ci and whatever. And finally you have aim ci. The point here is that this means that the coefficients of this matrix representation of T relative to these bases should be Aij. Right? Because if I were to take this and left multiply it by Aij, these are literally the entries. Or maybe it should be the other way around. Ji perhaps. Well, we'll write it like this. So this is going to be my A. Right, so I want to think of this as the output of a matrix vector multiplication. Okay, so for instance, look at the first entry. I runs from 1 to n, which means ai1 runs from 1 to n this way. Okay. So I guess I should have used ji there to match with our standard notation. Should be ji. Nope. Ji. Okay, yeah, that works. So 1i, then 2i, and then mi. Okay. So now, you see, for this entry, I'm running over all entries of the input vector, C1 to Cn. And likewise, in order for this to be the first entry of the output, this side should run through the first row of A. So this is A1, 1, A1, 2, whatever. Okay. That is the only way I can get this linear combination in the first entry of the output. And essentially the same thing works. A21, A22, dot, 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 A2n. And finally, I'm going to have A, M1, A, M2, dot, 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 A, Mn. Now, just to reiterate, how did we come up with this formula? Well, first, what I did was I started with T of V. I'll write it here. Okay. Then I substituted, instead of V, this linear combo that runs over all i's. Here, beta i's are vectors, c i's are scalars. T is supposed to be linear. Okay, it's linear, which means I can distribute this over the linear combination. Right? So take this inside, inside. Like so. But then I said, well, for each beta, or rather for each I, T of beta sub I itself is a vector in W, which means that for each I should be able to write T of beta I as a specific linear combination of gamma j's. Okay. So take T of beta I, write this as a linear combo of basis vectors. Basis gamma, okay? And so you're going to have one index that controls the basis vectors of gamma, but also those coefficients are going to depend on the index I also. Because if you were to use a different basis vector, beta 1, beta 2, whatever, well, the linear combinations probably are going to be different. And so this probably is going to look like something like this. So this is I, Ci, and J, and then AJI, I should say. AJI, gamma J. That's what I did. And then I said to myself, Ci's are here scalars, AJI's are scalars also. And because ultimately I want to display this as a linear combination of basis vectors gamma, well, the outermost summation loop should be J. So I'm just reordering everything to get this. That's how I got it. And how could you index into each of these AJI's? Well, for instance, if I were to look at T of, say, beta 1, so if V itself were beta 1, for instance, C1 would be 1, C2 would be 0, and all others would be 0 also. So beta 1 in V would turn into the standard n by 1 matrix like this. And so, therefore, the corresponding numbers would immediately give me the first column of the matrix representation of A. I realize this kind of sounds perhaps more confusing than it is. Let's look at examples. I'll give you two examples. Slightly more complicated than the ones that we looked into yesterday. And the best way to really understand what is going on when you're experimenting, you want to take v and w to be the same and the bases to be the same as well. Now remember from yesterday, change of basis had to do with this passive transformation. And you could have purely active, purely passive, or mixed type transformations. I think I would suggest that understanding active transformations are a lot easier. In other words, it's better to first fix both v and w to be the same space and fix the same basis. So there's no passive transformation happening underneath the hood. For instance, let's think about polynomials. Let's bound the degree, say by 4 this time, or maybe 3. This was the vector space of all polynomials with real coefficients of degree at most 3. In other words, any vector here is of the form a0 plus a1x plus a2x squared a3x cubed. Okay, we had done this before. What's a nice basis for it? Oh, this should be a plus. Well, the standard basis is 1x squared and x cubed. As you see, any such polynomial can be written uniquely as a linear combination of these monomial polynomials. So sigma, this is the standard basis of this. And this has the polynomials 1x, x squared, and x cubed. From a calculus point of view, remember, if you were to represent any polynomial relative to the standard basis, that's essentially nothing more than the Taylor coefficients at 0, if you know what that means. Ultimately, if I were to represent an arbitrary polynomial relative to this basis, I get this. These we had done before the second midterm. I'm just reiterating because I'm going to look at matrix representation of a certain transformation. And so I'll write it here. Matrix rep of an arbitrary polynomial, arbitrary vector in P3 of an arbitrary polynomial P of x, which is, say, something of this form, a0 plus a1x plus a2x squared plus a3x cubed, relative, right, relative to the standard basis, is, well, this was the notation I was using. You can use whatever notation you want. Well, you look at this expression, and you're trying to store this in a 4x1, right? So this basis has 4 elements. The dimension of this is 4. You're trying to associate to this polynomial a 4x1. And how do you do it? Well, for the first entry, we can have 4 entries like this. For the first entry, you look at the scalar next to 1, that is a0. And then for the second entry, you look at the scalar next to the second basis vector, a1, and so on. a0, a1, a2, a3. Okay. If you want to be more, calculus conscious, you would write it like this also, or you can write it like this. which I believe in the problem set due this Friday, you're going to do something like this, actually. Okay. Doesn't matter that much. Well, I can think about the differentiation operation. It's certainly a differential. It's certainly a linear transformation from P3 to itself. Right, so differentiation. So P is sent to D of P, which is nothing but P prime. First derivative. What do I want? I want to store this D in a matrix. If this is supposed to be a 4-dimensional space and so is this, then that means that I'm trying to store D in a 4x4. I want to represent D as a 4x4 matrix. Represent D as a 4x4. Not only as a 4x4 in general, but also I want this representation to be compatible with this matrix representation for polynomials. In other words, if I were to take first a polynomial, differentiate it, okay, and then look at its matrix representation, I want that to be the same thing as first storing the polynomial in a matrix, then multiplying it with whatever this representation is. I want this to be, these two things to be the same, compatible with sigma. In other words, I'm trying to find the 4x4 that is the matrix representation of D from sigma to sigma. Essentially, I'm going to do this business, okay? This diagram I'm erasing over here. So if I start with an arbitrary vector, that is to say, a polynomial of degree at most 3, like this, okay. Thinking of this as an input vector for differentiation, if I differentiate it, right, what was the rule? Well, you'll cut these terms with x's. You take the exponent and put it next to x and decrease the exponent by 1. So this drops, then this becomes a1 and whatever. So this is p prime. a2 times 2 times x plus a3 times 3 times x squared. This is the output. Relative to the standard basis, this turns into a0, a1, a2, a3. Relative to the standard basis, the output polynomial turns into a1, a2, or 2a2, let's say, 3a3, and then 0. So in order for this whole thing to work, in order for my representation of differentiation as a 4x4 to work with all this stuff, what has to happen is that, well, it's the 4x4 that represents D should match with these two things. And so what I do is I look at this and I think of it as a matrix vector product. Trying to factorize it. Okay? How can I get this? Well, for this entry, for instance, I'm going to multiply this by this. The only way for this to work for any AI, right? So P is supposed to be an arbitrary vector, and this is supposed to work for any polynomial whatsoever. Well, what needs to happen is the entries should be like so. Okay? How about this? Well, to get this number, right, this is a second entry. I'm going to multiply this with the second row. How can I get this by multiplying this and this? Well, I have to have a 2 here and zeros else. Okay? There you go. This guy is what I'm looking for. I was able to represent differentiation as a 4x4 in a way that is compatible with sigma. So in my notation, this is this. See, now you get to say, oh, differentiation, or rather this matrix of differentiation is an echelon form, right? It's not invertible. Its determinant is 0. You can talk about the determinant of the differentiation, for instance. Its rank is 3. Nullity, therefore, is 1. Okay, you can talk about all these things. Meaning, once you can sort of rewrite whatever crazy linear algebra you have into matrix algebra, now you can use all the tools that you've learned so far in this class. Yeah?
Is this matrix like scalable? Like if you have to do a 5x5, would it just be a 4? Like in that case?
Yeah, in fact, people would, very good point. You can also talk about infinite dimensional matrices, because if I didn't sort of put this restriction on the degree, and sometimes you may want to sort of leave that as is, you may want to keep it sort of flexible. You can sort of represent the collection of all polynomials as infinite by 1 matrices. Standard basis is 1, x squared, x cubed, dot, dot, dot. Now it's an infinite dimensional space. Never mind. You just do the same thing. Okay? In which case, you can again talk about differentiation. And now it would look like this. Okay? Now it's an infinity by infinity matrix, but in any event, the pattern is clear. This is essentially upper triangular, and in fact, the only non-zero entries are like this: 1, 2, 3, 4, whatever. Then zeros. Okay, zeros. This is not the end, of course. We can talk about essentially polynomials with infinitely many terms. These are what are called essentially analytic functions. So power series, you can differentiate power series, whatever. So you can keep sort of adding more and more bells and whistles to this whole business. Many of the, how to say, formalism starts breaking down if you're using infinite dimensional spaces. Infinite dimensional spaces really require that you get more comfortable with calculus and stuff. Okay, and that's why we're not going to use that. But in a sense, even there too, it's like in the world of infinite dimensional spaces also, you look at 2270 and you're like, oh, I have this nice theorem, whatever, and you're trying to get something similar. You're trying to get a similar calculation. Okay, yeah, good point. Does this make sense? Any comments or questions about this? Yeah.
Is it possible to
go from, say, a 3, how do I put this, like from p less than or equal to 4 to 3, or vice versa?
Yeah, you could have done this. Yeah, your colleague is suggesting, I know that when I differentiate a polynomial of degree at most 3, I'm going to end up with something of degree at most 2. So why do I need to keep that extra 0? I can put a 2 here. Everything works, but this time your matrix representation is going to be 2 by 3, or rather 3 by 4, which corresponds to this. Yeah, you're just getting rid of this zeroed out thing. Yeah. It just works beautifully, the whole thing. It takes a while to convince yourself of this. Okay. I'll give as an exercise to come up with the matrix representation, again, relative to sigma, in the case of P3, of, let's say, translation by 1. We had talked about how that's a linear transformation also. Take a polynomial, translate its graph by 1 unit to the right. That's a linear transformation. What is its matrix representation? It's a very good exercise. I might even put it in the next problem set, actually. Write it here. Compute the matrix rep of translation. Take the graph, move it sideways, whatever. You have something like this, move it by 1 unit, now we have this. In other words, take a p of x and turn it into a p of x minus 1. Still a polynomial, it's a linear transformation. Okay. I'll talk about one more example in the context of matrix spaces. Now, in computer science, if you try to take a rectangular matrix and store it in a column matrix, that's typically called a vectorization, or flattening. It has a bunch of different names. Because you're sort of breaking the matrix-matrix product structure, in a sense, if you reshape your matrix, but it's still a linear transformation. So let's say we're looking into the space of 2 by 3 matrices. So this is my wild vector space out there, okay? What's a standard basis? Well, it's these guys. That's the standard basis for this space. Any 2 by 3 can be written uniquely using these guys. Okay? And so I'll write it like this: A11, A12, A13, A21, A22, A23. What is this? Okay, it's kind of getting confusing, but ultimately this is going to store your 2 by 3 in a 6 by 1. And what it's going to do is, for the first entry, you're going to look at the coefficient of this guy, that is just A11. Then the coefficient of this, A12, and so on. A22, A23. This is called vectorization or flattening or reshaping. It has a bunch of different names. essentially, if you're studying LLMs, whatever, tokenization is something very similar, actually. Flattening. In terms of data structures, essentially what you're doing is you're taking an array that has two indices. You're sort of squishing it into an array that uses only one index, ultimately. OK. And so, for instance, what I can do is well, let's take the transpose. Of course, if I were to take the transpose of a 2 by 3, now it's going to be a 3 by 2. So maybe I should have used 2 by 2s here. I apologize. It's going to come out easier. So now I have 4 dimensions. Some of these vectors drop out, like so. That goes away. That goes away. I have this and this. These go away, and these go away. It's just going to come out nicer. Same idea. I want to think about, let's say curly T is transposition. Okay. So if I start with a wild vector, A, B, C, D, that's something out there, apply transpose. Now it is ACBD. That's how you take the transpose of something. Relative to the standard basis, ABCD, the input matrix is ABCD. Relative, again, to the standard basis, the output matrix is ACBD. Which means that the matrix representation of transposition relative to the standard basis is nothing but a permutation. Right? I'm just permuting these two entries. Up 0, 0, 0, 1. It's 1, 0, 0, 0, 0, 0, 0, 1. And then I want here 0, 0, 1, 0. Here I want 0, 1, 0, 0. Transposition is nothing but a permutation, you see. Pretty nice. Any comments or questions about this? Okay. You're going to encounter some problems in the next problem set. That's going to be after the break. But that's all there is to it. And now I think all you need to do is to calculate certain things just to convince yourselves that things really work. In this line of business, of course, what ends up being the craft of the whole thing is, well, you're given a weird vector space, and you're trying to do something, okay? And the point is to realize which basis makes calculations down the line easier. That's the real art of this whole thing. Once you can store your complicated vector space or linear transformation into matrices, you can just import linear algebra and do whatever you want. But depending on how you do the importing, linear algebra might be easier or harder to finish.
Yes.
So
is that technically a different basis than our final basis?
You can, in principle, you can use different bases, yes. But what I'm looking here is what I said was this. It's like, I'm just going to fix the same basis for the input and output so that there's no sort of passive transformation that is compositing what I'm seeing in the matrix.
I guess my question is pretty simple. It's
Yes.
just that basis we have written up there, that would be a different basis than we're using for input and output simply because we have a column versus a 4x1 versus a 2x2, correct?
Well, I mean, I'm thinking of this V as like a vector space out there. And so when you're trying to come up with a basis for a vector space, your vectors should be, so this should be a set in V. When I start like this, I don't quite have any access to any other type of a vector. And if I'm trying to come up with a basis for V, I have to take vectors in V. Like from the perspective of, so I look out into the world, I see 2x2 vectors, right? 2x2 matrices as vectors. And so that's all I can use for a basis. But once I fix a basis, now I can flatten whatever thing I see in the world, turn it into something computational. Maybe you can rephrase what you're asking.
Yeah, let me think about that. Thank you.
Okay, yeah, we'll discuss it. We'll discuss it further. Okay. It's not very sophisticated, the idea. It's just that it's, for whatever reason, it's very confusing. At least it was for me. Okay, so that's the end of relativity, and we have a couple minutes. That's okay. Eigenstuff. This is chapter 5. The major import, or rather export, of this class. This is chapter 5. You see, no one ever discusses whether or not linear algebra is useful, and it's essentially because of this. Eigenvalues and eigenvectors, okay? These are the two important things you should learn, and here's the definition. All this relativity stuff I'm going to set aside. For most purposes, again, linear transformations are matrices, whatever, okay? For us, it's not going to matter, at least for a while, this relativity and basis conscious thinking. While it is important to be able to be aware of which basis you're using, whatever, it's also sort of cumbersome and like tedious, whatever. So typically, you would just assume, oh, there's a standard basis and all that. Okay. So let A be an n by n matrix. Okay. I'm going to call the eigenequation. You know, it's something serious if it's German, the word you're using. Eigenequation. In older textbooks, you might see sort of characteristic vector, whatever, instead of eigen. Of A is the equation. Let's write it like this. Ax equals lambda x. Where x is an n by 1, so x is an n-dimensional vector. And lambda is a scalar. Okay. Fairly innocent looking. What does this mean? It means even though this A is a square matrix and sort of complicated whatever, I'm looking for some vector x such that applying A to it is this much simpler operation of multiplying it by some scalar. Okay, that's what essentially means, what this means. Now the one complicated matter in this is that in general this may not be solvable if you're using only real vectors and real numbers. But this is so important that you always want this to have solutions. And it just turns out to be the case that if you allow complex vectors and complex scalars, this always has solutions. So technically, x is, maybe it has imaginary numbers, whatever, and lambda 2 is possibly a complex number. Why? Because, like I said, this is so important in all areas of math or physics or sciences that you always want to have solutions. And it just so happens to be the case that in physics, you end up needing to use complex numbers. Okay. So when I write it like this, for any fixed lambda as a scalar, even though these are technically complex numbers, we can just pretend that these are real numbers, and then we'll see how to handle complex situations later. So in this equation, if you fix lambda, now this is a linear equation. But in principle, both x and lambda are unknowns. So if both of them are unknown, this is not quite a linear equation. It's a second order equation because you're multiplying two unknowns. And so what you do is, as you're trying to solve this, you typically go first for a solution of lambda, and then you sort of try to solve for x. So here, I'll write it. Both lambda and x is unknown. X are unknown. Okay? Since lambda is a scalar, we have a nice method to first sort of separate that out and solve for lambdas. And then, based on each solution, lambda, we're going to solve for x. Any solution of this, in terms of lambda, is called an eigenvalue. Okay? And any non-zero x that solves it likewise is called an eigenvector. I'll not write it because I'm running out of time. We're going to continue looking into this later. Thank you. All right, let's start. Good morning. We'll take attendance today. So we can now really focus on the main topic of this week, namely eigenvalues and eigenvectors. And I told you that the rest of this course is going to be essentially just downstream from these ideas. Everything that we've done so far, computational methods, determinants, rank, row reduction, all these things ultimately are going to be helpful in computing eigenvalues and eigenvectors. But somehow I feel like the flavor is slightly different, and things are going to get slightly more advanced in a sense. And it's going to get slightly more geometric. Okay, so I'll do this. I'll first define everything on that right board. And then we'll take our time, do examples and so on. I should also mention the first part of this course, row reduction, whatever, I tend to fast forward just so that we can spend more time on what is to come. So spectral theorem, for instance, or singular value decomposition, all these things, these I think take a lot longer to digest. And so we're going to slightly slow down compared to the first couple of weeks of the course. Okay, so none of this relativity stuff. We're back to the way we were treating matrices and transformations, whatever. I'm going to take n by n's, okay? Let A be an n by n matrix. Okay, I can think of it as a linear transformation from Rn to Rn also. essentially using the standard basis. The eigenequation of A is this, is AX equals lambda x, where x is a vector and lambda is a scalar. X is an n-dimensional vector in Rn, and lambda is a scalar. Your first instinct should be to try to go for real solutions. That is to say, vector x with x1, x2, whatever, all real numbers, no funny business with the imaginary numbers, whatever. But it might happen that for some matrices A, you need to use complex numbers. Okay? Imagine, for instance, the quadratic formula for degree 2 polynomials. Well, sometimes it has real roots. Sometimes, though, you have to use complex numbers to get roots. Okay? Same thing is inherited here. So I'll just write it. Initially, you want x and lambda to be all real coefficiented, all with real coefficients. X and lambda to be real, but under certain circumstances, which we're going to discuss later, you may end up needing to use complex numbers also. But in certain situations, you may have to use complex numbers. Okay? And just to give you an idea, typically complex numbers start showing up if some sort of a rotation is involved. Okay? Okay. Okay. That's the eigenequation. Now, I'll transition to examples, but I'll introduce the notions of eigenvalue and eigenvector also, and in fact, the rest of these. First things first, you should realize immediately that in order for this equation, or rather its solutions, to say something about A, well, x has to be non-zero. Because if you were to think of x as the zero vector, vector with all zeros, well, no matter what lambda is, this is always going to be satisfied. So x equals 0 doesn't really say anything about A. Doesn't say anything. Doesn't signify anything. Therefore, really you want to look at non-zero x solutions to this equation. Any such solution is an eigenvector. And, okay, if x is non-zero and lambda is arbitrary, then, I should also say lambda is arbitrary and they solve the equation. If they solve the eigenequation, you call x an eigenvector of A, lambda an eigenvalue of A, and sometimes you might also see x is an eigenvector associated to lambda, and lambda is an eigenvalue associated to x. Then call x eigenvector lambda eigenvalue of A. Typically, the first thing you should try to do is what is called you should set up the so-called characteristic equation. And so instead of trying to solve both for x and lambda simultaneously, what we're going to try to do first is to solve for lambda for the scalar, and then we're going to condition on different lambda values. Okay? So the characteristic equation of A is this. Okay, it's going to look bizarre. I'm not going to tell you why it works, but we're going to see first that it works in examples. Well, you look at lambda times identity, so that's a diagonal matrix with lambda on the diagonal, minus A. Take the determinant of this, okay, set it equal to 0. This is the characteristic equation of A. Lambda is an eigenvalue if and only if it solves the characteristic equation. So, solutions lambda of the characteristic equation is the same thing as eigenvalues. Okay, that's the big idea. Okay, bunch of new terminology. I want to do examples. How do we sort of look into examples? What is the sort of general method? First, we try to do it for 2 by 2s. Then for higher dimensional things, we look at matrices of special type, maybe diagonal, whatever. Okay? So let's start with 2 by 2s. I'll give you a 2 by 2. A is 1, 6, 5, 2. Like this, from the textbook. Okay. First, I want to solve for lambda, this eigenequation, which means first I'm going to set up the characteristic equation and solve it for lambda. What is the characteristic equation of A? Okay, 0 equals determinant of lambda I minus A. Okay, you open this up. What does it say? This is the determinant of lambda 0, 0, lambda minus this matrix. Okay. Consolidates. Again, just to reiterate, when you have a linear combo like this of a square matrices, the determinant of the linear combo is not the linear combo of the determinants. You cannot just distribute. Okay? Determinant is more complicated. It's not a linear transformation. So you have to just consolidate everything and run through the definition of the determinants. Okay? You have to do it like this. Or otherwise, I mean, it's going to give you something, but it's going to be wrong. Okay. Now I expand this. What was the determinant of a 2 by 2? This by this minus this by this. And so lambda minus 1 times lambda minus 2. Okay, this by this minus this by this. Okay, continue here. Expand everything. Because ultimately, why am I looking for this? Ultimately, I'm going to solve this characteristic equation for lambda. Sometimes you might be able to eyeball lambda values such that this is 0. But in principle or in general, I would recommend that you go through the whole thing and sort of simplify things. So here I have lambda squared minus 2 lambda minus lambda plus 2. Okay, so this is the first part. And then this gives you minus 30. Consolidating, lambda squared minus 3 lambda minus 28. Okay. Can you perhaps try to split this by just looking at it? Some people, yeah.
-7 lambda, also 4 lambda.
Yeah, so there's a method to sort of just eyeball in certain situations. What your colleague is suggesting is right. How do you do this? So I'll just do it on the side. You see sort of like a quadratic like this. Okay, especially if you're polynomial, and you see this is a polynomial in lambda. If your coefficients are integer, this is kind of like a nice rule. What I do is this. I sort of split into 2, and I'm trying to sort of guess 2 integers whose product is this, whose sum is this. Okay? I'm looking at 28. What are the integer factors of this? 1, 2, 4, 7. Okay, 7 against 4. This by this is going to give me 28. But then when I add these up, I want to get minus 3, which means this should be like this. Okay? That's sort of the trick. If you're not familiar with this trick, you can go with the quadratic formula, of course. I would suggest that you get comfortable with factoring polynomials, at least in lower degree. In any event, you split it like so. So finally, once you consolidate everything, you have that the characteristic equation is lambda minus 7 times lambda plus 4 equals 0. I was able to compute the characteristic equation like so. Okay? Again, if you're not familiar with this method, then you need to use the quadratic formula. You need to do something because you need to solve for lambda there. I'll write it. Or quadratic formula. Quadratic formula is going to work for 2 by 2s at least. It's not going to necessarily work for higher dimensional matrices. Okay. This is my characteristic equation. Eigenvalues of A, based on this box, is exactly the same thing as the zeros of that equation or the solutions of that equation. This has exactly 2 solutions. Lambda equals 7, lambda equals minus 4. So let's say lambda 1 equals 7, lambda 2 equals minus 4. Zeros of the characteristic equation. Any comments or questions so far? I want to slow down, like I said, because this stuff is really important. And as you see, we're sort of using everything we learned so far to calculate things at this stage. Okay. So once you solve for the eigenvalues, now you want to solve for eigenvectors, because ultimately what we're interested in is the eigenequation, okay? I want to solve this. I was able to solve for lambda values. Now I'm going to go ahead and condition on the lambda values. That is to say, I'm going to plug in lambda equals this number, lambda equals that number, and then just solve for x. I'll do it here. Eigenvectors. Associated to lambda 1, which was 7. Go back to the eigenequation. Okay, A is fixed, that matrix over there. Fixing my lambda to be 7 and solve for x. 1, 6, 5, 2. Say x1, x2 equals lambda x1, lambda x2. I just expanded, wrote it in coordinates, for x. Oop, x1, x2. Again, remember, if I were to plug in x1 equals 0, x2 equals 0, clearly that would be a solution, and this should be 7. Maybe I should have left it like this, actually. Scalar times this. If x1 were 0 and x2 were 0, this would be clearly satisfied, but that doesn't signify anything, okay? So you're looking for x non-zero. I don't want this to be the 0 vector. I'm never going to call the 0 vector an eigenvector, okay? 0 vectors are never eigenvectors. Okay, how do you solve such a thing? Well, you just expand this if you want and then do some sort of a row reduction. What you can do is you can basically send this to the other side and consolidate and just essentially use this matrix. Okay, I'll do this once. Taking this to the other side, I have 0, 0 equals seven zero zero seven x1 x2 minus 1652 x1 x2. Okay, I can factor out the x1 x2, because that's one of the rules of matrix algebra, like so, minus 1652, this whole thing, x1 x2. Consolidating, I have here 1 2 by 2, so 6 minus 5 5. So solving that, okay, is the same thing as solving this equals this. In other words, I'm trying to get the null space of this matrix, right? How do you do that? Well, you can do it in multiple ways. Let's use the augmented matrix thing, the method. Right? So you put it like so. Turn it into an augmented matrix. Let's remind ourselves. And so I see, oh, you know, I can just divide this by 6 to turn it into 1 minus 1 and then 0 here. And then I can divide this by minus 5. Again, 1 minus 1, 0. And then add, say, the first row or minus the first row to the second row to get rid of it. You have 1, minus 1, and then 0, 0, 0, 0. Which tells me that the general solution of this system I was trying to solve is x1 plus x2 is 0, x2 free. Okay, do it like this. X1 equals x2. x2 free. Make sense? Now, given this, I'm going to choose as many linearly independent bases as possible in such a way that they're all non-zero, of course. When I see something like this, I gravitate toward choosing x2 to be 1 so that my matrix turns out to be 1, 1. Okay? One eigenvector is going to be enough insofar as the nullity of this matrix is 1. In this case, it is. So all I need is one eigenvector. And so say v1, which is 1, 1, is an eigenvector, evec, for lambda 1, associated to lambda 1, which is 7. Just to check it, what does all this say ultimately? I'm saying that for lambda equals 7 and v equals, or x equals 1, 1, that's a solution to the eigenequation. Let's just check it here on the side. So you see, one of the complications in this business is a lot of the calculations are going to have like multiple steps like this. So check. A times v1, what was that? 1, 6, 5, 2 times 1, 1, right? When I do this multiplication, this by this plus this by this is 7. This by this times plus this by this is also 7. So you see, it does solve the eigenequation. What does this mean? What does the eigenequation mean geometrically? Well, think of it like this. Here's R2. Question?
Yes.
Yes.
You might have already mentioned this, but could you said the v1 was 1, 1. Could it have been any combination of integers as long as they were equal?
Exactly. Yes. It's okay. So if I were to tell you, okay, so I guess what I tried doing here is I looked at this solution set and I came up with a basis. When I eyeball this, the nicest basis is 1, 1 for me. Yeah. If you want it, you could have used -1, -1, 15, 15, whatever.
And you just used the word basis. Is that an actual basis?
Yes. I mean, the set consisting of only this vector is the basis, if you want to be more proper. Yes. But yeah, so the nullity of this matrix is 1. Okay. Row reduce, 1 pivot. Rank is 1. Nullity is 2 minus 1 is 1. Basis requires only one vector. Very good. So what does this say, geometrically speaking? Well, this is a complicated matrix, you see. It takes 1, 0 to 1, 5, and 0, 1 to 6, 2. But somehow, all this calculation told you this. If you were to just look at the diagonal line, okay, the effect of A is rather nice. If you just focus on this diagonal line, applying A merely corresponds to stretching vectors by a factor of 7. Because 1, 1, now under A is going to turn into 7, 7. So you see, on the whole, A doesn't necessarily preserve the x-axis, right? It sort of takes 1, 0 to 1, 5, does something to it. Doesn't preserve the y-axis, but for whatever reason, it preserves the diagonal axis. Make sense? And what does it do along this diagonal axis? It stretches this line by a factor of 7. 7 eigenvalue stretch factor. Okay? Does this make sense? Comments or questions about this? Yes?
When you have the lambda, it's a scalar. How come you made it into the 2 by 2 matrix of 7, 0, 0, 7?
Yeah, because scalar multiplying a vector by 7 is the same thing as left multiplying the same vector by 7 times identity. Right? So do this matrix multiplication. Right? This by this, 7x1. This by this, 7x2. Make sense? Yeah. Any other comments? You might as well ask now because things are going to get more gnarly as time goes by. It might be, your question might be about a sort of straightforward calculation step or whatever. All of these are going to sort of come together here. Yes?
What does it do for the horizontal and vertical axes then, things that aren't directly the diagonal?
I mean, you can keep track of these as well. So if I have a 2 by 2 like this, what I know is 1, 5, the first column, is where A sends 1, 0, 2. So for instance, A takes 1, 0 to 1, 5. It was here before. It lifts it like this. Okay? And 0, 1. Okay. Second column is where A sends 0, 1, 2. So you see, it's even harder to visualize what A does to 6, 2. But what I'm seeing is the x-axis, x-coordinate is going to be somewhere here, and y is going to be somewhere there. Something like this. And in fact, as you look at this, the determinant of this is negative, okay? Right? Because 2 minus 30 minus 28, I don't quite care about the specific number, but it's a negative number. Changes orientation, which means if I had my face like this, see, if I apply A to it, it's going to turn this way. Flips orientation. So at large, understanding A or visualizing A is rather hard. But this eigenequation allows me to just focus on a certain slice of the space. In this case, this line. Along this line, A is a very benign transformation. Multiply by 7. Okay? Remember, for quite a while, I've been always saying, oh, diagonals are nice because they preserve axes and stuff. Having axes are very nice, okay? Along axes, if your transformation preserves an axis, along it, that means it's either expanding or stretching, or flipping the other way around, whatever. Which means along these axes, linear algebra reduces to college algebra, which is nice. You want to do college algebra if you can get away with it. Any other comments about this? Yes?
What if the nullity equals 0?
It will not be. Yes. Think about why. But yes. The reason why all this works is because I'm essentially forcing the nullity of this matrix to be non-zero. Otherwise, it wouldn't have any solution. Yes. We're going to talk about why this method works later. I just want to do examples for now. Yes?
Are there any cases where you can't solve for eigenvalues or eigenvectors? Are there any like special cases?
No, if you're allowed to use complex things. You can, in fact, think of it like this, okay? There are cases that have no solutions using only reals, and that's why people invented complex numbers. This eigenequation is so important that they might as well switch the number system. Okay? Yeah. We'll talk about examples of that too. We're still not done with this example, by the way. I just solved one eigenvector, found one eigenvector for this. I need to do the same thing for this guy too, you see? I told you these calculations end up being rather sort of lengthy. Yes?
I like kind of loosely follow. How does the characteristic equation actually, like how do we create this characteristic equation? Like I understand how we're creating this like scalar of the identity matrix, but I don't understand why we're taking the determinant of it.
Because ultimately I want a number, scalar. Once you take the determinant of a matrix, it's going to turn into a scalar. And also, it's a polynomial always, polynomial in lambda. So I want characteristic equation to be some polynomial equals 0. I want to say characteristic equation of A is the, or the eigenvalues is the zeros of a certain polynomial that I associated to A. But you can sort of try thinking about why I would even look into determinant being 0. That's really saying to me that this guy is not invertible. In other words, nullity has to be positive. I need that because I need a non-zero vector. Yeah. We're going to talk about all that too. Let's not worry too much about why this works for now. I did some calculations going through characteristic equation, solve the characteristic equation to get eigenvalues, plug in the eigenvalue to get eigenvector. I got one here. And I plugged it into A, and I was able to see that this indeed solves the eigenequation for A. We're going to talk about why this works later, maybe on Friday. Any other questions about what I did so far? Okay, let's finish up. I need to look at eigenvectors for lambda 2 as well, minus 4. What do I do again? I look at the null space of a certain matrix. And so when I plug in lambda equals minus 4, I get this. Write it like so. Well, I'll take my time this time. Minus A, 1, 6, 5, 2, subtract. Minus 5, minus 6, minus 5, minus 6. Okay. You see, once you sort of look into this matrix, after you plug in the eigenvalue, it's going to look rather low rank, okay? You're going to see redundancies pretty much from the get-go, generally speaking. Okay? That's the matrix whose null space I'm looking into. But certainly, this is the same thing up to a row reduction as this. I can get rid of these two just to make sure I'm doing things correctly. So I'm looking at the null space for this. Eyeballing, I see that this is an eigenvector. So put here 6, put here a 5. This doesn't give you 0. Put a minus here. Now it gives you a 0. Okay. That's an eigenvector associated to lambda 2. Again, let's check over here. A times v2, I want to see is some scalar multiple of v2. One, 6, 5, 2 times 6 minus 5. I hope this is going to work. 6 minus 30 is minus 24. Yes. 30 minus 10 is 20. Okay. Simplifying, divide everything by minus 4. I got this. You see, this is yet another solution to the eigenequation. Geometrically then, what is happening is this. I have one axis along the diagonal that A stretches by a factor of 7, okay? And another axis, which is this, 6 minus 5. Seems like it's not really significant, but for the purposes of applying A, it is very significant. Along it, A is a scalar multiplication. So typically people, instead of drawing two planes, would draw one plane and sort of display the effect of A on the one thing. So one of them is like this. What do I need? 1 to 6. Try to draw it in perspective, like so. Okay, 1, 2, 3, 4, 5, 6. 1. And then 1, 2, 3, 4, 5, 6. Minus 1, minus 2, minus, oh, not that. Minus 1, minus 2, minus 3, minus 4, minus 5. Let's do it like this. Here is V1. Okay. And here is V2. This guy. I start with this. When I apply A to this picture, V1 gets stretched by a factor of 7. Okay? In other words, you can also think about what A does to this whole line. It is stretching this line by a factor of 7. Okay? So maybe you can do it like this. This line gets expanded. The other line also gets expanded by a factor of 4 this time. It doesn't get expanded as much. And it also gets flipped. Okay? So maybe you can draw it like this. If I start with the initial picture, okay, I apply A to it. That's sort of my time progression, if you want. Now, this is expanded by a factor of 7. This guy is expanded by a factor of 4, and then flipped. It's still in the same line. Okay? And I keep applying A to it if you want. And this guy gets stretched more and more. Okay? Imagine this. It's like things are sort of escaping. And things that, on this line, still get expanded by a lesser factor, 4, and every time it also gets flipped. Okay, start like this. Make sense?
When you found V2, oh, you just had, or how did you find that? Because you would have ended up with negative 5 x1 equals 6x2, and then x2 is free.
So, okay.
You could have just made x2 1.
I mean, there's multiple questions. So ultimately, to get an eigenvector for lambda 2, I need to get a vector in the null space of this. Okay? And so when I write it out, right, minus 5 times x1 minus 6 times x2 equals 0, and x2 free. Yes. Because I like integer vectors, I sort of eyeball this and I say, well, I'm just going to pick this to be 6, pick this to be 5, so that this is 30, this is 30, and then I fudge the sign so that everything cancels out. Yeah. Does this kind of make sense? Like, if you can't see this right from the get-go, you just go through the motions and slowly sort of write down things. But you know, it's more preferable that you can just eyeball things at this stage. Okay. This was the main sort of reason in the previous problem sets you were seeing all these tedious calculations and so on. Without actually going through the motions, you can't really get fast. There's a bunch of tricks like this. What it is that you keep doing calculations, and eventually you're fed up with the amount of calculations, and your brain starts coming up with shortcuts. That's kind of how I kind of got better at these kind of things. Okay. Any other comments or questions about this? Yes?
Will one of the variables always be free?
Yes, at least one, yes. Because otherwise, let's think about this, okay? If one of the variables were not, or if none of the variables were free, that would really mean that the nullity is 0, right? Because the number of free variables is the same thing as the nullity. If the nullity is 0 of a square matrix, that's the same thing as saying that the matrix is invertible. If that matrix were invertible, there would be no non-zero vectors that solves this eigenvector equation. But I want a non-zero vector. What is mysterious at this stage is why this characteristic equation business works. Okay? We'll talk about that later. This is, in practice, how you sort of compute these kind of things. Okay? Look at the matrix, set up the characteristic equation. Solve the characteristic equation. These are the eigenvalues. Plug in these different values one by one. Solve for the associated system. That gives you eigenvectors. Okay? And unfortunately, this is, in general situations, this is the fastest method. Of course, there are certain tricks that we're going to look into. But ultimately, things like the spectral theorem, at the very least, tells you things about these eigenvalues. Not necessarily their specific values, but whether or not perhaps they are repeating or whatever. Okay? So we're going to get to all that in the coming weeks. Yes?
So I just noticed, why is it flipped? Like the 6 and the negative 5? Because theoretically, if you plug in like 5 for x1 and 6 for x2, like that'd become true.
No, but then you're comparing 25 to 36. You want to crisscross.
Oh, yes. Okay.
Yes.
I see. I get it. All right.
Yes. Very good. You want to crisscross these kind of things. Any other comments? Okay. Let's try to start one example. I have 2 minutes. We'll start one. I want to stick to 2 by 2s still. Say I'm looking at rotation by 90 degrees. Just by thinking about it, eigenvectors are going to correspond to lines that are invariant. But under a rotation, there cannot be any line, which means there's some funny shenanigans happening here. 0, minus 1, 1, 0. Characteristic equation is 0 equals lambda here, 1 minus 1 here. So I get this. Uh-oh, this doesn't have any real solutions, you see? That's why we're going to use complex numbers for rotation type of things. This has no real solutions. So the eigenvalues of A is going to be solutions of this. And if you want, you can literally define I and minus I to be the eigenvalues of this specific matrix. So plus or minus I. See? Because this idea of an eigenequation is so important that we don't want to say, this has no solution, okay? This equation is so important that we might as well just transition to complex numbers. It's an investment to make, of course, but it's well worth it based on physics and other things, okay? That's it for today. We're going to continue on Friday. Thank you. All right, let's start. Good morning. We're going to keep working on determinants today. Do more examples. Yesterday, on Wednesday, the example that I mentioned was this rotation by 90 degrees, and we realized, oh, this guy doesn't have any real eigenvalues. But you know, if you're allowed to use complex numbers, then you can still talk about eigenvalues and eigenvectors. I'm going to pause that for a second because for now I think it's good to think of that as a pathological case. What else should I say? Oh, I've extended the deadline to the problem set. It's due Sunday now, which was due today originally. And midterm 2 grades are up. I'm fairly happy. The average is slightly less than last time, and like 85, I think. No perfect scores this time, but there's a lot of at least like 13 A's and 10 A minuses or something. So I'm fairly happy. The key is up on Canvas also. It would be good to have a look at it for the purposes of perhaps the final. So let's do a recap of what we've been talking about so far. We said eigenstuff, right? We have an n by n. If I have an n by n, the first thing that we want to look into is this eigenequation. Ax equals lambda x. Okay, you want to solve this. Here, x is a vector. Lambda scalar. But since x, so if you were to choose x to be the 0 vector, no matter what lambda is, this is always solved. It doesn't give you much. So you really want x to be non-zero. And non-zero vectors that are the solutions to this are called eigenvectors. And arbitrary scalars, lambda, that solve, again, the same equation, are called eigenvalues. So this is the eigenequation. Eigenvalue, solutions lambda. Eigenvector, solutions x. Again, non-zero. So they come in pairs. To each eigenvalue, there's at least one eigenvector and vice versa. In principle, you know, there could be many eigenvectors associated to the same eigenvalue. So typically, you want to look at the set of solutions. You want to look at the basis for it and stuff like that. And so we said, oh, in this case, because both the vector x and the scalar lambda are unknown, and since we're in that equation, we're multiplying two unknowns, that by itself is not quite a linear equation. So we say, oh, because of that, we're going to first try to solve for the lambda, and then we're going to condition on the different lambda values. So this is where this idea of the characteristic equation comes into play. I'll write it here. And how do you do this? You look at lambda I, lambda identity, minus a. That's, again, a square matrix. You look at the determinant of it, and you set it equal to 0. That's the characteristic equation. Determinant of lambda I minus a. And 0, we said eigenvalues is the same thing as zeros or solutions to the characteristic equation. So lambda is an eigenvector, eigenvalue, sorry. If and only if it solves the characteristic equation. Okay. Now, I didn't mention why this really works on Wednesday, but let's try to reason. Ultimately, what I'm really interested in is the eigenequation, ax equals lambda x. And I want to solve that for x non-zero. Rearranging is the same thing as solving lambda I minus a, that's a square matrix, applied to x being 0. But you see, I'm only interested in non-zero solutions to this. In other words, I want a non-zero x to solve this for some arbitrary lambda. Okay? In other words, in order for there to be an eigenvector, what needs to happen is that this has to have a non-zero solution. But if you think about this, this is nothing but the equation for the null space of lambda I minus a. In other words, an eigenvector associated to lambda is the same thing as a vector in the null space of lambda I minus a. I'll write it here. So x, eigenvector associated to lambda is the same thing as saying x in the null space of lambda I minus a. And since I want a non-zero eigenvector, well, the null space of this specific matrix should have a positive dimension. If it were zero-dimensional, I wouldn't be able to solve this equation for a non-zero vector. In other words, I want lambda I minus a to be not invertible. That can only happen if its determinant is 0. And that is why we're looking at the characteristic equation, this specific equation. So we first set up this characteristic equation to fish for lambda values that makes lambda I minus a non-invertible. So first we solve, therefore, the characteristic equation for lambda. That gives you a bunch of scalars. Then we condition on these scalars to get eigenvectors associated to these lambdas. So the method is, first solve the characteristic equation for lambda. Step 1, solve for lambda. Step 2, condition lambda to be any one of these values and solve this equation to get eigenvectors. Condition on specific lambda values to compute x eigenvectors. Okay. On Wednesday, I gave one example with a 2 by 2, but you can do this with any n by n. So let's try to do one more example. Instead of looking at a general 3 by 3, for instance, I want to first look at matrices of simpler type. What are the matrices of simpler type? The best type of square matrices are the diagonal matrices, okay? So that's what you want to focus on. Let's do a 4 by 4 perhaps. Say A is this diagonal matrix. 1, 2, minus 3, 5. I want to find all eigenvalues and all eigenvectors associated to these. Actually, I'll change this just a little bit. I'll put a 2 here. 2, 2, minus 3, 5. So, what is the characteristic equation? Characteristic equation is 0 equals determinant of lambda I minus A. Okay. So now, of course, this I means it's a 4 by 4 identity matrix. So I'm just looking at this determinant. Lambda minus 2, lambda minus 2, lambda plus 3, lambda minus 5. Okay. Now I want to compute this determinant. Well, this itself, no matter what lambda is a diagonal matrix. So its determinant is nothing but the product of the diagonal values. Okay? I'm not going to expand it though. I'm just going to write it out loud, write it explicitly. And so what is this? This is lambda minus 2, 2 of them, times lambda plus 3, times lambda minus 5. Okay. Eigenvalues is the same thing as zeros of the characteristic equation. In this case, you see, because we started with a diagonal matrix, the characteristic equation came out to be a split polynomial like this. That's yet another reason why diagonals are so nice. You don't need to sort of factorize it. Characteristic equation comes out factorized already. And so what are the zeros? Lambda 1 equals 2, lambda 2 equals 2 also. So you see you could have repeated eigenvalues. Lambda 3 is minus 3, lambda 4 is 5. Okay? This is always going to work. Whenever you have a diagonal matrix, one of the tricks that we were looking into was, the determinant of that diagonal matrix is the product of the diagonal entries. Next up, you see, also the eigenvalues are the diagonal entries. That's a trick also. Okay? It's a very useful thing. So you don't need to go through this. Whenever you see a diagonal matrix, you know, without going through all this stuff, oh, the diagonal entries are the eigenvalues. Okay. So you record these. Now, that's the end of step 1. I want to now condition on each of these specific values of lambda and solve for eigenvectors. Eigenvectors for these two. For these, I need to look at lambda I minus a for lambda equals to 2. So, right, so this is, you can just look at this matrix, 0, 0, 5, minus 3. I need vectors in the null space of this. Well, when you look at this, or maybe let's do it explicitly this time. So lambda I minus a, x1, x2, x3, x4 is what? 0, 0 here. Multiply the third by 5. And multiply the fourth by minus 3. I need this to be in the null space. So I want these to be equal to 0, which means x3 has to be 0 and x4 has to be 0. x1 and x2 are free. That's the general solution set. Okay. But I want to turn this into sort of like a basis if you want. If I have x1 and x2 free, what I can do is, well, the simplest choices for me is 1, 0, 0, 0 and 0, 1, 0, 0. Okay. Eigenvectors associated to lambda equals 2. Okay? Yeah?
I'm confused why you swapped the 5 and the negative 3.
I didn't swap it. I just did this algebra thing. So I'm just looking at this expression, right? So plug in lambda equals 2. 2, 2, 2, 2 minus this thing. So these are going to cancel out. 2 minus minus 3 is 5.
Oh, so you did minus. Okay. You
Yes.
just didn't write it down. So
Yes, yes, yes. Yes. And likewise, 2 minus 5 is minus 3, and that goes there. By the way, some people, instead of looking at lambda I minus a, look at a minus lambda I. It's the same thing. I like subtracting the matrix, because that way the characteristic equation comes with, plus with the highest lambda exponent. You can do it the other way around, in which case, this expression could be slightly different, but it works just the same. Okay, and you see, here's yet another sort of shortcut. With diagonals, we said diagonal entries are always eigenvalues, and furthermore, the standard basis vectors are going to be always the eigenvectors also. Right? So lambda 1 comes from here, 1, 0, 0, 0. 0, 1, 0, 0. Okay? You can immediately see this too. For instance, if I were to take A and multiply 0, 0, 1, 0, well, that's going to give me just 0, 0, minus 3, 0. It's just going to cut out the third column, which means that an eigenvector associated to minus 3 is going to be 0, 0, 1, 0. Okay? So eigenvex for lambda 3, which is 3. Well, you can just take v3 to be 0, 0, 1, 0, based on what I just said. If you take a, multiply it with this, well, this is just going to tell me what the third column of a is. And the third column of a is nothing but minus 3 times v3 to begin with. So I'm done. And finally, eigenvectors for lambda 4, which was 5. v4 is going to be then 0, 0, 0, 1. That's the end for this. So you see, diagonal matrices are also very nice for the purposes of eigenstuff. Diagonal entries are eigenvalues, okay? And the standard basis vectors are eigenvectors. Okay. I'll leave it like this. There are certain complications that start creeping up eventually. This is a fairly nice situation. Okay. Any comments or questions about this example? So you see, if you had only diagonal matrices, this computation of eigenvector stuff would be fairly nice, but that is not usually the case. And here's the unfortunate situation. You can't quite use row reduction to compute eigenvalues also. I mean, you can, but it's not going to be convenient. Okay, so we need more tools, more advanced tools for that. Okay, so that's an example with a diagonal matrix. Another case is when you have lower or upper triangular. Let's do an example with that. I'll change this to this perhaps. I'll use a 3 by 3 this time. 1, 1, 1, 2, like this. Okay. Now this is upper triangular. First things first, again, you set up the characteristic equation. Zero equals determinant of lambda I minus a. Now this I is 3 by 3. You expand this. Okay. Lambda minus 1, lambda minus 1, minus 1 here, and then lambda minus 2 there. Like this. You see, this time again, this matrix that depends on lambda is still upper triangular, and we know that the determinant of such a matrix is a product of the diagonal entries. So again, the characteristic equation is going to pop out already split. Two of lambda minus 2s, lambda minus 1, and then 1 lambda minus 2. Okay? What are the eigenvalues then? Lambda 1 equals lambda 2 equals 1, lambda 3 equals 2. These are the eigenvalues. Okay. Same as before. Now I want to condition on different values of lambda. Lambda equals 1 would give me eigenvectors for the eigenvalue 1. Eigenvectors for lambda 1 equals lambda 2 equals 1. Right, I'm just looking at lambda I minus a. If you plug in here lambda equals 1, you get 0, 0, minus 1 here, and then you have another minus 1 there. So lambda I minus a then is this. Minus 1. Again, I need a vector for the in the null space of this, or multiple, if possible. Right? And so let's do it once. I'm trying to solve this times x1, x2, x3 equals 0, 0, 0. Well, what are the solutions to this? Well, this is going to give me minus x2, so x2 has to be 0, and so is x3. x1 is free. Okay?
So can I
Yes.
stop you for a second?
Yeah.
Why is the lambda I minus a, why is the top middle one a negative 1? Because shouldn't it be negative 1 minus negative 1?
No, no, no,
Or-
but this is a.
Oh, I see, okay.
Yeah. Yeah, so either you take this or you plug in this expression whatever your eigenvalues.
Okay.
Yeah, so let's do it. Let's write it explicitly. Yeah, good question. I'm not doing anything new, but somehow it takes a while to sort of get accustomed to this procedure, I realize. It's like multiple steps, I think. That's part of it. That's what I'm computing, okay? So 0, minus 1, 0, 0, 0, 0, 0, 0, minus 1. Yeah. Okay. Which then I put here because I needed one vector at least in the null space of this. Set up this equation for the null space. Get the general solution. x2 and x3 are 0. x1 is free. So v1 equals 1, 0, 0 is an eigenvector for lambda equals 1. Okay. So you see, even though for the purposes of calculating eigenvalues, upper triangulars are just as nice as diagonals, when it comes to then further compute eigenvectors, now things are typically more complicated. Why do I say it's more complicated? If you remember with the diagonal, if I had repeating eigenvalues, I had the same dimension for the null space associated. In other words, in the previous example, for instance, eigenvalue 2 was repeating, and I was able to find two eigenvectors that are linearly independent associated to the same eigenvalue. So the exponent here I saw in the characteristic equation matched with the nullity of the associated matrix. Okay? In general, though, what might happen is that even though, for instance, in the characteristic equation, you have this exponent, once you start trying to calculate eigenvectors, you end up not being able to compute as many linearly independent eigenvectors. Okay? We're going to talk about that later too. But that's an issue. There's some terminology. So you would say, for instance, the eigenvalue 1 for this matrix has algebraic multiplicity 2. It repeats for the purposes of algebra. But when you try to come up with eigenvectors that are linearly independent, you are not able to compute eigenvectors associated to the same eigenvalue with the same number. In this case, you would say the geometric multiplicity of the eigenvalue 1 is 1. We're gonna talk about this terminology later, probably after the break. For now, we're just computing things. The other eigenvector is, eigenvalue is 2. Again, I set up this equation. Right, so lambda I minus a. What is this? Let's try it. 2, 0, 0, 0, 2, 0, 0, 0, 2 minus a. Okay. Now this turns into what? 1 minus 1, 0. And then 0, 1, 0. And then 0, 0, 0. Okay. I need a vector in the null space of this. Let's compute it on the side here. Okay, so if I multiply this by x1, x2, x3, I get what? x1 minus x2 in the first coordinate, and then x2 in the second coordinate, and then 0. 0 in the third coordinate. I need this to be 0. In order for this to be 0, well, x2 has to be 0. But if x2 is 0, x1 has to be 0 also. Which means the general solution to this is x1 equals 0, x2 equals 0, x3 free. I'll write it here. That's the general solution, which means v3, 0, 0, 1 is an eigenvector for lambda equals 2. Okay? Any comments or questions so far? Yeah.
Sorry, remind me, how did you get from, on the left-hand side, from that a equals down to the determinant of the lambda minus 1 equation?
Well, this is the characteristic equation. Like, you need to know this definition.
Okay.
I'm going to just set this up, expand everything, because this involves some determinant. Your expanded determinant gives you ultimately a polynomial in lambda.
I guess I'm just a little confused why the top middle is -1 over there.
This?
Yes.
Well, okay.
I'm used to like the diagonal part, that it's just like the lambda like minus whatever
Yeah.
the diagonal is, but
Yeah.
what if it's a non-zero number, like in the triangle? Because like the previous equation, you had like all zeros, but the 2, 2, 5, and 3.
Yes.
So it's easy to compute like it's the lambda minus 2 and whatnot.
Yes.
But why is the middle one -1?
You mean this or this?
The top one, yeah.
Well, I mean, because,
-8.
so, yeah, let's write it again. Yeah, I guess precisely because of this, some people write it the other way around. I like writing it like this, but you can do it that way too. So, okay, let's expand this. So I'm saying 0 equals determinant of lambda I minus a. This is determinant of this. Consolidate. Okay. Lambda minus 1, 0 minus 1. Yes. Like this. 0, 0. Yeah. Yeah.
Also have a question.
Yes.
I think I missed when you said, so you said that if the polynomial representation of lambda had that value squared,
Yes.
we'd end up with two vectors or two-dimensional basis in the null space?
You would want that.
You would,
Yes.
you would want that.
Yes, that's the best case,
But that's not always true.
as in this example. In this example, this eigenvalue repeats, 1 repeats, but you don't have the same number of linearly independent eigenvectors associated to it. Yeah, we're going to talk about that later. For now, we're just computing, okay? Yes.
How come x1 and x2 are 0 here?
Because to get an eigenvector associated to this number, I need a vector in the null space of this. So when I set this up, x1, x2, x3 has to be so that the outcome is 0. How can this be 0? In order for this to be 0, this has to be 0. In which case, this has to be 0.
Got it.
Which ultimately doesn't say anything about the third one. Yeah. Okay. And again, we have a lot of choices here. Instead of choosing x3 to be 1, I could have chosen it to be pi, whatever. So you have infinitely many eigenvectors, but the point is, what is the dimension? How many linearly independent ones are there? And when you're sort of trying to get for eigenvectors, I would suggest going for the simplest looking ones. Okay. Any other comments or questions about this example? Okay. Let's do one more. Let's do a nastier example. Okay. So it's going to be 3 by 3. Now it's not going to be one of these nicer types, diagonal or triangular. This is from the textbook. 6, 2, 1, 6, 2 minus 1, 8. Now this is going to hurt, okay? Let me see if I see any pattern here. Well, we might be able to get away with some sort of simplifications, but ultimately it's not going to be as nice as these cases. First things first, characteristic equation. 0 equals determinant of lambda I minus a. Let's do this slowly. So, okay. Determinant of lambda 0, 0, 0 lambda 0, 0, 0 lambda. Okay, minus this guy. Like this. Just to reiterate, when you have a linear combo like this of two matrices, and when you're taking the determinant, you don't get to distribute the determinant over, okay? That's going to fail. I'm telling this because experience shows that students do make this mistake. You have to consolidate everything. There's no sort of simpler way of calculating this at this stage. need to consolidate. Okay, lambda plus 1, lambda minus 6, minus 2, lambda minus 1. Oh, there are no lambdas here. Yes, okay. Then minus 2, 1, lambda minus 8. Okay. Now I need to compute this determinant. Now you see there's some sort of a pattern that I'm kind of trying to see here. Maybe I can do this, use this to get rid of this, whatever. But you have to be very careful in this context, because once you're doing row reduction, which it is allowed, even if you have a parameter, now it's like, imagine taking this and knocking out this guy, but that means you're going to have some lambda here and stuff. Because you have a parameter, doing this row reduction ends up being rather messy. Okay. So you see, row reduction is not super optimal for eigenvalue calculations. We need different things. Okay, but at least in 3 by 3 we have a bunch of rules that we can use. I'll use this triangular rule, right? So this is plus this. This is plus, and then this is again plus. Now the other way around, this is a minus, minus 12 times lambda minus 1. This is a minus, plus 2 times lambda minus 8. And then this is a minus also, plus 6 lambda minus 4. Okay. Ultimately, I'm going to go for zeros of this. So I need to somehow consolidate all this stuff. At this stage, though, I would suggest that you don't expand this. You want to sort of like simplify. You want to sort of expand these perhaps and stuff. So this is now polynomial algebra. Lambda minus 1, lambda minus 8. I think it's OK to consolidate these, plus 24. Then expand these linear terms, minus 12 lambda plus 12, plus 2 lambda minus 16, plus 6 lambda minus 24. Okay, I'm looking at it to see some cancellations. I see some cancellations. That's nice. So this 24 cancels with this guy. I can consolidate these two into a minus 4, and I can consolidate these also, and then I'm going to have to open this cubic, unfortunately. Or maybe maybe I'll be able to get away with it too, actually, without completely opening it. We'll see. So this is a matter of careful calculation, as you can observe. Okay. I'll continue here. I'm going to leave the cubic as is for now. Okay, lambda minus 4. Lambda minus 1, lambda minus 8. Then what else do I have? That's an 8 lambda minus 4 lambda. Okay. And here I have a minus 4 also. Okay, so you see, that's nice. I think I can get away with not completely opening this up, because I can factorize. Oh, wait. No, I guess I do need to open everything up. I thought that was a plus 4. Just to check. Yeah. Yeah, we have to just compute this then. Okay, there are rules for expanding these, but what you can do is you can just expand this first and then do it once more. Lambda squared minus 5 lambda plus 4 times lambda minus 8 minus 4 lambda minus 4. Expand once more. Lambda cubed minus 8 lambda squared minus 5 lambda squared plus 40 lambda plus 4 lambda minus 32 minus 4 lambda minus 4. Okay. Consolidate. Lambda cubed, that's my only cubic term. And then quadratic terms are minus 13 lambda squared. Now I have, okay, this 4 lambda cancels with this, plus 40 lambda. This cancels with this, plus 40 lambda, and then minus 36. Okay. So my characteristic equation is that cubic polynomial in lambda equals 0. I started with 0. The solutions to this are my eigenvalues. Okay. Just come to terms with the fact that it is as complicated as this. At this stage, this is the best we have. So we need to figure out how to solve this equation. But just like with the second order equations, what you can do is, at least for polynomials whose coefficients are integers, you look at the 0th order term, the term with no lambdas, you look at its integer factors, and you sort of like just test them out. So for instance, with 36, I have 1, 2, 3, 4, 6, 9, right? And then I have minuses possibly. And so you just test these out. You're trying to sort of find at least one factor here. Okay, so factors of 36 is 1, 2, 3, 4, 6, 9, and in fact 18 and 36 too if you want, and with pluses and minuses. So you want to start simple. For instance, if I were to fish for lambda equals 1, you just need to just plug it in and see if it works. So 1 minus 13 plus 40 minus 36 equals not 0, I believe. Yes, this is not 0, so it doesn't work. You need to test out other things. Lambda equals minus 1. Now this is minus 1 minus 13 minus 40. Okay, that's also not 0. Let's do 2. 8 minus 13 times 4 is 52, I believe, plus 160 minus 36. Doesn't seem like it's going to work. That's also not a factor. Let's try to see minus 2. Starting to feel like I made a mistake somewhere, but we'll march on. This was not a not a factor either. So now I have minus 8, minus 52, minus 80. This is also not 0. That also doesn't work. Let me just check the textbook. 2 is supposed to be an eigenvalue to this, which means I made a mistake somewhere. Uh-oh. Let's see. 8 minus 52.
I believe 4
Oh.
times 2 is 80.
Yeah. This should be 80. Thank you. Now it works, you see. You don't need to look further. So lambda equals 2 is a solution. So lambda equals 2 is, if it's a solution, that means that you should be able to factorize this as some degree 2 polynomial times lambda minus 2. So you divide. Just like with integer division, whatever, you can just divide 2 polynomials. Okay. So this is lambda squared, lambda cubed minus 2 lambda squared, subtract. Now I have minus 11 lambda squared plus 40 lambda minus 36. That's minus 11 lambda here, minus 11 lambda squared plus 22 lambda, subtract. 18 lambda minus 36. That's exactly 18 times this. So this is the other factor. That means we're still not done, you see. Oh, but the time is out. Time is out, unfortunately. We're almost done. We computed the eigenvalues. One of them is 2. The other one is minus 2. The other one is minus 9, or rather plus. OK. We're going to continue after the break. Thank you. Have a nice break. I'll see you in 2 weeks.